Okay, so we're going to start, working with some review topics, and this one is going to be on density and pressure. Let me get the basics going here. So this is going to be a quick review of the main ideas. First of all, I think we're all fond of density is mass over volume. And what you have to remember is that you have to consider both the mass and the volume when you're working a problem. Because if two objects have the same mass but different volumes, then they will have different densities. Likewise, if two objects have the same volume, they take up the same amount of space, but they have more mass or less mass in that space, then we've got some change in density. So our volumes and our masses, you have to think about both. You can't just say, oh, there's more mass, so there's got to be more density. It does not always work that way. So some couple other quick things about this is generally when we're working with fluids, instead of finding mass, because it's difficult, like gases, liquids, it's hard to put them on a balance. You can't just put them on a scale a lot of times. You have to measure them in another object and then remember to subtract off the mass of the cup or the bowl or whatever's holding it. When working with fluids, it's a lot easier for us to use density times volume gives us the mass. So a lot of times in an equation where you would have mass, you replace it with density and volume. Now remember, the Greek letter rho is the symbol we use for density, and it's the volumetric density. We can use density actually in lots of ways. You can do mass per area or mass per length, but in our case with fluids, we're talking about mass in a certain space. So with density, a couple of things. Obviously, things float if density of the object is less than the density of the fluid that it's dropped into. You sink if density of the object is greater than density of the fluid. And you suspend if density of the object equals the density of the fluid. This one, you may recall, is called neutral buoyancy. So neutral buoyancy, floating means that you have a liquid and your object is, some part of it at least, is out of the water or the mercury or the iodine or whatever we're working with. Sink, of course, would be the object's down here and the fluid height's up there. Neutral buoyancy, this suspending, is when you put an object in here and it just stays right there. Just sits there. Doesn't go anywhere. It doesn't sink. It doesn't float. It just sits there. We call that neutral buoyancy, and that only occurs when the object and the fluid have the exact same density. So that's probably something you may have forgotten. Since the beginning of the year, we haven't used that much. So we call that a suspension or a suspended object, or a neutrally buoyant object. So those are some terms. And then the other thing that we're going to work out with here at the beginning is, I don't want to do pressure yet, is the idea of the specific gravity. And specific gravity is the density of your material over the density of water. So if they ask for specific gravity, they're talking about the density of your material compared to the density of water. Now, the density of water, you do not have to have this memorized. They give it to you on the test, but it is 100 kilograms or 1,000 kilograms per cubic meter, or it is 1 gram per cubic centimeter. You will also see it written as grams per liter, things like that. So the common ones we're going to use in physics are the kilograms and the grams. So if I have an object whose specific gravity, let's say of my ceramic mug that I'm drinking tea out of, the specific gravity is 0.890, then that tells me that its density is 890 kilograms per cubic meter, or 0.890 grams per cubic centimeter. So the idea of specific gravity is so that if we can quickly figure out we have water, that's a quick way for us to figure out what we have in terms of our densities. The other thing you need to keep in mind about the floating and the sinking is this. The percentage below fluid level, so that kind of looks like it's got an E on the end of my fluid. The percentage below fluid level is equal to the percent of fluid's density. So for example, I'll come down a little bit further. If we had an object that we measured that it was 34% was below the line for water, that tells me that the density of this material is equal to 34% of water's density. We usually use that when we're talking about a situation with one object we know and the other one we don't. So for example, molten gold, and if you look this up, I don't know what this number is, but I'm going to go with it's 19.8 kilograms per cubic meter. So if I had lead with 92% below fluid line, so in other words, we have a container, and in here we have molten gold, that's liquid gold, and I put lead in there, make lead darker, have a blob of lead in there. If it's 92% of it is below the fluid line, then 0.92 times 19.8 would be my density of lead. Now, that's not correct. I just made those numbers up to illustrate. So the amount underneath the water line or underneath the fluid line will tell you the percent density that it has compared to the fluid you drop it in. So that's the first part. That's kind of just a review of density. Now, the second part is pressure. The definition of pressure is it is force divided by area. So its unit is the Newton per square meter. But since we didn't want to have to write that every time, we called this unit the Pascal, and the symbol we use is a capital P, lowercase a. So pascals, newtons per meter squared, is our standard unit for pressure. Now, there are three kinds of pressure. There is gauge pressure, there is atmospheric pressure, and there is total pressure, which we call absolute pressure. AP will call it absolute pressure. So AP is going to go with this term. But what they really mean is the total pressure. So let's talk about what this is. Atmospheric pressure is just a number for the air pressure due to, the atmospheric pressure, the pressure due to the weight of the air. So this is the pressure due to atmospheric weight. The atmosphere's weight on whatever area that we happen to be talking about. Now the number that's given on the AP test is 1.00 times 10 to the 5th newtons per meter squared. That is 1 ATM, that is 1 atmosphere. They may give you another value sometimes on the test. Around here, the atmospheric pressure is about 101,500. So it's 1015, 101.5. So you just have to roll with what atmospheric pressure they ask you for. The formula sheet has a value for that, and so if you're asked to solve any problems with it, you should use the one that is on the formula sheet. Now, gauge pressure is the amount of pressure on top of atmosphere. So, for example, when I have a car tire, and I tell you that the car tire has 35 psi, that would be pounds per square inch. The 35 is the gauge pressure, and it is in addition to the atmosphere's weight. So, in this situation that we have up here, let's look at this one. If I wanted to know what the pressure, the gauge pressure is, the gauge pressure would simply be due to the weight of the lid. The atmospheric pressure would be all the air that's above this particular cup or mug or container. So gauge pressure is the extra pressure due to additional weight or additional pressure being added to a contained fluid. So typically when you're talking about a gauge pressure, you're talking about a contained fluid, like the pressure inside a balloon or the pressure inside a soda can before you open it. So it's an additional pressure in addition to atmospheric. Which brings us to total pressure. So pressure absolute is the pressure gauge plus the pressure atmospheric. So pressure gauge plus pressure atmospheric is 1 times 10 to the 5th. Well, let's write it in the order that I wrote it. Sorry. It is density, gravity, times height. This is your gauge pressure. And then your atmospheric would be 1.0 times 10 to the 5th. So gauge pressure depends on density of the fluid. Whoops. Let me fix that. It's a little messy. Density of the fluid. Wow. What have we got going on here? I think I've got off the screen a little bit. So gauge pressure is density. Come on, buddy. Density of fluid times gravitational acceleration times the depth in the fluid. So, if I have a pool, let's say I have a pool of water, and in my pool of water, I have a boat. Here's my boat. And some of the boat is underwater level. It's going to have a little hole. It's under the water level. And I've got a boat sitting there. The pressure at the surface is going to be pressure atmospheric. Okay? At the surface level, it's atmospheric. The pressure down here at the bottom is going to be pressure of the atmosphere plus density times gravity times height plus the pressure from the boat. So in this case, the density times gravity height would be water's density times gravity times depth. This would be the height we're talking about. And then the pressure due to the boat would be weight of the boat over the area of pool. So we would do the weight of the boat gets distributed everywhere across the surface. So we're talking about just plain pressure or gauge pressure. Every time you go deeper in a fluid, you increase the gauge pressure because you have an additional weight or an additional layer of fluid sitting on top of the level that you happen to be at. So even if we have something let's see, one more page. Even if we have something that looks like this, if I have a nice big pool here, and I have, I don't know, let's say I've got a slab here. If I wanted to measure the pressure at the top and the pressure at the bottom, the two measures of the pressure at the top and the bottom of this object would be different, because one of them is under a depth of fluid that has this height, and the other one is under a depth of fluid and object that is this height. So the pressure at the top will be less than the pressure at the bottom, and the easiest way to figure those would be gauge pressure is less than gauge pressure. They both have the same atmospheric pressure, but the difference of the distance in the fluid, like this layer of water versus this layer of water, will have different pressures on the level because they're at different depths in the water. Okay, so that's our quick review of this. So what are we going to do with this? What does it look like? Okay, well, let's look at number 6. And if you want to follow along and pause and think about and work this question before I work it, that's quite fine. And I think that's a really good idea. And then you can hear the explanation that goes along with it. So I'm going to do number 6 on the problems to your right. And it says 3 fishing bobbers all float on top of water. They have the following relationships. A and B have same mass and same density, which means even though they say they have different shapes, they have to have the same volume. Because if they have the same mass, so density equals mass per volume, density is the same, mass is the same, requires that you have to have the same volume. Now B and C, though, B and C have the same size and same shape. So B and C are same size, which means same volume. So when I hear same size, I need to think same volume. And they have the same shape, but that doesn't tell me anything about density or mass. Okay, I don't know anything about that. And then last but not least, they tell us that the mass and density of C, C's mass and density are less than B's. Okay, so first of all, what I got to figure out is, what do I think this looks like? Well, A and B, if they're all floating on the water, A and B are floating at the exact same depth. So here's A, here's B. They might have different shapes, but they have the same density, same mass, and same volume. B and C have the same volume. It floats, but maybe that means that down here, C has the same volume, but we don't know anything about its density or mass. And then we're going to attach a weight to each of them. Who displaces the most amount of water? Well, let's see. If C's mass and density are less than B's, but they have the same volume, okay, that means that B and C have the same volume, so when they're under the water, they're both going to displace the same amount of water. So B and C are going to displace the same amount of water. What's going to happen for A and B now? A and B are same density, same, so they all three, when you pull them out, whatever they look like, whatever weirdness shapes they've got, when you pull them out, they are all going to displace the same amount of water. Okay? So the density of C is littler, but because it takes up the same volume of water, it's going to displace the same water. Now, this brings us to a key piece, as we review. And I want to put this in big bold print here. Objects that float displace their own weight. This will be asked about on the AP test. Objects that float displace their own weight, meaning that force buoyant up and force gravity down are equal to if you're floating. Objects that sink displace their own volume. So if we sink, we displace volume. If we float, we displace weight. So that's the big takeaway, and that's the big shortcut that we want to keep in mind when we're thinking about this. Okay, so on number 9, let's look at number 9. And you can pause, feel free to pause before I answer. As a rock sinks deeper and deeper into the water of constant density, what happens to the buoyant force? Well, the buoyant force, and we're going to talk about this more later, the buoyant force depends on the fluid you move, not the object. So the fluid you move is not going to change. As the rock sinks, it's going to take up the same amount of space the whole time. And since it takes up the same amount of space, it's going to displace its own volume. So the buoyant force will not change, even though the rock is falling to the bottom of the fluid column. Okay. Let's see. Here's a question like I was telling you about, number 12. A liquid has a specific gravity of 0.357. So what is its density? Well, its density for number 12 would be 0.357 times the density of water, which is 1,000. And so it would be 357 kilograms per meter cubed. That would be a question like you might see on specific gravity. Okay. Now, anything else I want to do about that before we go to forces? Nope, I think that's it. So just keep in mind that when you're working on these, and here's one, we'll do forces later. We do forces actually on our next video. Keep in mind that objects that float displace their own weight. The buoyant force balances their weight. But objects that sink displace their own volume. So they take up the same amount of fluid as they take up in air. They're more dense, they have more mass in that area, but they have the same fluid volume. So just be aware of that when you're working problems. Okay, going to stop for there, and then we will call this on the next one. Hope you have a good day.